Yeah, let's start. I want to start on time. So, okay, 3 people. Yeah, that's perfect. Feel free to turn on your video. 4 people. Nice. All right. Anyways, so today I'm gonna discuss how to count trees, and so the subject is the matrix tree theorem. Which, so previously I gave you just some kind of nice exact formulas for some particular families of graphs, like the complete graphs, and that's pretty much it. Yeah, the complete bipartite graphs as well. So today I'm gonna do this for arbitrary graphs. You give me a graph, and then I'm gonna give you an efficient way to compute the number of trees. So what kind of trees am I gonna compute? Well, so here's the definition, which we had before. So if G is a graph, let's say G has vertices and edges, then a spanning tree of G is a tree T with the same set of vertices but a subset of edges. E prime is a subset of E. So you give me an arbitrary graph, and then I choose all possible, connected subgraphs without cycles. And so the question is, so let me introduce the notation. So let kappa of G be the number of spanning trees of G. So and so the question is going to be, question is, given an arbitrary graph G, how to compute kappa of G. And so the formula is not going to be as beautiful, it's just n something to the power of something else, because you're allowed to have arbitrary graphs. But still, there is going to be a nice formula. And so what do I mean by nice in this case? Well, usually I just say that this is beautiful based on my aesthetic choices. But this time the niceness is going to be the efficiency, right? So what I want to do today is polynomial time. For those of you who like computer science, they know what it is. If you don't, then, well, basically, if you give me a graph G on a million vertices, then I don't want to, if I want to count these spanning trees, generating all of them is inefficient. It's going to take exponential time, I think. Exponential in the number of vertices, let's say. But I want polynomial time. And so here's the way to do it. Let me introduce, I'm going to do it using matrices. So, and my matrix of interest today is going to be the Laplacian matrix. So let G be a graph, and I want the vertices to be labeled from 1 to n as usual. Then the Laplacian matrix, which is going to be noted L of G, is given by, so L of G, let me denote the entries by Lij. Then Lij is basically, so let me write down the definition. So this is an n by n matrix. And the entries are -1 if Vi and Vj are connected, and the degree of Vi on the diagonal if Vi, well, if I equals to j, and 0 otherwise. Okay, so basically I have a square matrix. Yeah, it's square. So the degree of V1, degree of V2, the diagonal just contains the degrees of all your vertices. And then in off-diagonal entries, if you have row I and column j, then this entry is -1 if I is connected to j by an edge in your graph. So that's it. That's the Laplacian matrix. And so, by the way, I guess I should explain the name. How many of you know about the Laplacian operator from like PDE? Okay, one, two people plus. Okay, yeah, okay. Let me explain. So, yeah, let me do this on the side. So in PDE, we have the Laplace operator, which, you know, we have a function f, and then delta f is by definition f, the second derivative, is the sum of second derivatives of your function f, essentially. And so if f looks kind of like this, then the Laplacian is negative. If f looks like this, then it's positive. And if it's a saddle, then it can be 0. So the cool thing about the Laplacian, one of the cool things is that it describes the heat equation. So heat equation, which is so you think of f, your function f, as some sort of, you know, temperature at every point of your space, and then if you look at the evolution of temperature as time kind of, well, you start with some temperature at every point, and then you just kind of let it diffuse. So the temperature is going to change, and the way it's going to change is that it's just going to be proportional to the Laplace operator. And so if you have a point where the temperature looks like this, right, then as time goes on, the temperature at this point is going to go down, right? Because the neighboring points are going to kind of pull it down, and similarly, you know, if it looks like this, then the temperature is going to stay the same locally. Anyways, what happens for the Laplacian matrix here is that, so let's say G is a graph, right? And then so the vertex set is bracket n, and then f, you can think of f as an assignment of temperatures to your vertices. F is f1, f2, all the way up to fn. These are the temperatures at vertices. Then so you can think of it as a vector, right? So you have the, yeah, let me even try to copy this. You have the Laplacian matrix, which looks like this. So some -1s off diagonal. That's the Laplacian matrix of G. And then if you multiply it by a vector, you know, f1, f2, maybe fj, etc. So you have j here, and then you have I here, maybe. So, well, yeah, let's say I is somewhere else. So you multiply each row of the Laplacian matrix by the column vector of the temperatures. So what happens is, well, what happens is if you multiply, so if you take the Laplacian matrix of G times f, you get a new vector of temperatures. By the way, this is all just a kind of an analogy. I'm not trying to say anything particularly important here. But so you multiply a matrix by a vector, and then you want to find the, let's say, the ith entry. Then it's going to be what? It's going to be, there's the degree of vi times f sub I. Degree of vi times f sub I, and then you subtract the sum over all ij in E, I not equal to j. So for all of those off-diagonal entries, you get -1 times f sub j. So minus f sub j. Okay. That's just, I'm just multiplying a matrix by a vector. But notice that the number of terms here, right, the number of non-zero terms is equal to the degree of my vertex I, right? Because it's, I have the degree here, and then I have exactly this many -1s in the same row. So I can rewrite the sum as the sum over I, j in E of fi minus fj. And so if you think about it, you have your vertex I, and then you have a bunch of neighbors. I, j1, j2, etc. And then you have some temperature here, and then you have some temperatures at the neighbors. And the point is that this Laplacian, if you apply the Laplacian operator, it tells you how much the temperature at I is going to change. Because if I has, because the kind of the rate of how temperature changes is it's proportional to the difference of two temperatures. So each of these edges kind of provides an exchange of heat between the corresponding two vertices. And so that's sort of the point I'm making, is that the Laplacian operator is the discrete version of the Laplace operator from PDE, and it sort of describes. You can actually talk about, you can take a graph to be the lattice of atoms, and then the actual discrete Laplace operator is going to describe how the temperature changes. Does it make sense, or is it? Anyway, I was kind of in doubt whether I should give this analogy or not, but I decided that I need to justify the name. This is unrelated to what I'm going to say next. So what am I going to say next? Well, next I'm going to ask, what is the determinant? So question, what is the determinant of the Laplacian matrix of G? So you give me a graph. What is the, let me even give a couple of examples. Maybe, let's say the Laplacian matrix of K2, right? Well, I only have K3. So for K2, I have K2 looks like this. Vertices 1 and 2. So I have a 2 by 2 matrix with the degree of each vertex is 1. 1, 1, -1, -1. And then the Laplacian of K3 is, I have a 3 by 3 matrix. My graph is a triangle. 1, 2, 3. So the degrees are equal to 2. And I have -1, -1, -1, because everybody is connected to everybody. And I can even try maybe a 4 cycle. 1, 2, 3, 4. Laplacian of the 4 cycle is all degrees are equal to 2, but then 1 is connected to 2 and 4. 2 is connected to 1 and 3. Yeah, so the matrix looks like this. Anyways, what is the determinant? Not sure why, but is it 0? Yeah, thank you. That is a great guess. Indeed, if you look at this matrix, then the determinant is 2 minus 2, or sorry, 1 minus 1, which is 0. And here, maybe it's slightly harder, but the determinant is, what is it? 8 minus 1 minus 1 minus 2 minus 2 minus 2, which is 0. Yeah, so the determinant is 0. Claim the determinant of the Laplacian matrix of G is 0. And so what is the reason? The reason is that the row sum is 0. Right. So if you just take the sum of all rows, then each entry is going to be 0, because in each column you have the degree of v, and then you have exactly as many negative ones in the same column. Right. So like this row plus this row plus this row is going to be 2 minus 1 minus 1, that's 0. Yeah, anyways, each column is going to contribute a 0 entry. So and that's a problem, right? Because if the row sum is 0, that means that, yeah, let me write it as sum of rows, because sum of rows, and that's this is a linear dependence between the rows, and therefore the determinant is 0. So that's the whole proof. And by the way, any questions so far? All right. So okay, so how is it all related to trees? And so far I have constructed a matrix, which is kind of stupid because it's determined as 0. Let me now state the theorem. Matrix tree theorem. So let G be any graph, and then let, so here's the result. I'm not going to just take the Laplacian matrix, but I'm going to take the truncated Laplacian matrix. So I'm going to take I'm going to remove the let L0 of G be obtained from L of G by removing the last row and last column. Then the number of spanning trees of G is equal to the determinant of L not of G. And in particular, if you know about matrix algorithms, the determinant can be computed in polynomial time. So I'm not going to prove the theorem, even though I could have. The proof is pretty accessible if you know about linear algebra. But let me just give a couple of examples and make sure that the theorem is correct. So let's say I want to take these examples. So maybe if I want to compute L0 let's say L0 of K2. And then I just need to erase the last column and the last row. So the determinant is going to be equal to 1, which is, yes, there is a unique spanning tree of K2. Now if I want to compute L0 of K3, then again I'm going to erase the last column and the last row. And the new determinant is going to be 4 minus 1, which is going to be 3. And as you know, there's 3 spanning trees of the triangle. Is it an inductive proof? Well, no, actually, the proof I know is using the proof uses the Cauchy-Binet formula. So yeah, if you know what it is, then there is like, you can multiply the incidence matrix by its transpose, and then use this formula to kind of very easily deduce the statement. But if you, yeah, I don't know an inductive proof actually. That's interesting. Yeah, I have to think about it. But off the top of my head, that's the only proof I know. You can look it up. It's in Stanley's book, and probably on Wikipedia as well. Not sure. Yeah. Anyways, let me try to do the 4 cycle, and then maybe some other examples. Yeah, let's before even I do the 4 cycle, let's try L0 of K4, which is gonna, so I'm gonna all degrees, right? K4 looks like this. So all the degrees are equal to 3. I'm removing the last row and column, and well, the determinant is going to be equal to 27 minus 27 minus 1 minus 1 minus 3 minus 3 minus 3, right, which is 27 minus 11. Okay, that is 16. So you see the same sequence, right? N to the n minus 2. That's the number of spanning trees of, it's the Cayley's formula. This is n to the n minus 2. Which you can actually, yeah, there's another proof of the Cayley's formula using just linear algebra. So you can deduce Cayley's formula from the matrix tree theorem by just computing basically the eigenvalues of this matrix. Those are, those require some skills from linear algebra, but it's pretty easy to compute the eigenvalues of a matrix which has all negative ones except for the diagonal. Yeah. Anyways, and let me even not do the 4 cycle. Let me try. So the point that I'm making is that if you ever need to compute number of spanning trees for whatever reason, you can just use a computer. That's going to be, so let me try, maybe what I'm going to try is a 6th cycle. Right, and because we know the answer for the 6th cycle, one, two, three, 4, 5, 6. So the Laplacian matrix of G is going to be 2, 2, 2, 2, 2, 2. Negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. It's going to look something like this. And actually, so the point is that you can just Google this, and I'm actually gonna try to show you a demonstration. Not sure if it's gonna, yeah, let's see. Okay, so I have some website which just the first thing in Google. And here you have the Laplacian matrix. So if you compute the determinant, let's see, determinant. You compute the determinant and you get 0, right? You get 0 because that's the Laplacian matrix. But if you okay, that doesn't work. All right, I don't know why it doesn't work. Yeah, okay. So if you remove the last row and the last column, and then you compute the determinant, then you get 6. You get 6, and that is exactly the correct answer, right? Because for a 6th cycle, there are 6 trees which you can get by removing any of the edges. So yeah, you can now take huge graphs, and it's gonna work very fast. And anyways, I think that's cool. So that's what I wanted to tell you. If you have any questions, let me know. Otherwise, I'm just gonna do something completely different for the rest of the class. All right, no questions. Okay, let's continue. I'm actually going to continue to count trees, and this time I'm gonna talk about rooted plane trees. So basically, if you want to count spanning trees, then the matrix tree theorem is the answer. And now I want to count trees which have more information. Like here, I'm going to talk about plane trees, which means that they are drawn in the plane. And the actual answer is going to depend on how you draw a tree. So let me try to give you a definition. First, I'm going to draw a picture of a rooted plane tree. Maybe something like this. So here's an example of a rooted plane tree. So the root is here. That's the root. And yeah, let me write down the definition. A rooted plane tree. And I'm going to give a recursive definition. So is a tree drawn in the plane with a, so there is going to be a distinguished vertex, right? There is one vertex is with a chosen root vertex. Let's say root vertex R, and it's going to be connected to V1, V2, etc. up to Vk. So V1, V2, all the way up to Vk. And the key point is that these neighbors of the root are ordered, right? The order matters. And then the last condition is that each of these individual VI's has to be the root of a smaller rooted plane tree. And each VI is a root of a smaller rooted plane tree. And that's why this definition is recursive. I'm defining rooted plane trees in terms of smaller rooted plane trees. And actually, yeah, we're going to talk about trees a lot, and if you ever have to program them, then this recursive approach is actually very efficient. So, okay, that's the definition of a rooted plane tree. And an implementation of that, and let me actually write it down as well. In other words, so a short version of that definition, a rooted plane tree is a tuple of smaller, it's an ordered sequence of smaller rooted plane trees. So I'm going to write it as T is equal to T1, T2, etc. up to Tk. So the idea is that this whole thing is T, and then to specify T just means that you have to specify each. This is like T1, this is T2, and this is all the way up to Tk. And then each of them is going to be also a tuple of smaller trees, and etc. So and that's very well suited for a computer. Okay, and now I have to tell you, because I want to talk about plane trees, and now I have to tell you when are two plane trees the same, because I want to count them, and I want to count them. So in other words, I want to. So okay, let me try to. So let's say you have one rooted plane tree, and then you have another rooted plane tree, which may be, let's see, maybe I want to swap the first and the second subtrees. Then the point is that these are not the same trees. Even though if you know about graph isomorphism, then you know as unlabeled trees, these are exactly the same, right? You can I just swapped the two subtrees, but I want, because they're drawn in the plane in a different way, I want to think of them as two different trees, and I want to count them separately. So and the kind of the formal definition using this notation here is that two rooted plane trees. Well, let me just write it down like this: T1, well, T is equal to T1, T2, all the way up to Tk, and T prime is T prime 1, T prime 2, all the way up to T prime m, are isomorphic as rooted plane trees if and only if k is equal to m, right? So the number of subtrees has to be the same, and again, this is going to be a recursive definition, and T1 is isomorphic to T1 prime. So I'm going to denote isomorphic as this kind of equality with a tilde. T1 is isomorphic to T1 prime, T2 is isomorphic to T2 prime, and etc. Tk is isomorphic to Tk prime as rooted plane trees. Okay. So in other words, if I want to compare two rooted plane trees to check whether they are the same or not, first of all I check that the root is connected to the same number of vertices in both of these trees, and then I check that the first subtree is the same as the first subtree, which in this case it is not. So so this condition is not satisfied, and therefore these two are not the same trees. But yeah, the short version of this definition is that they are the same if you draw them in the plane, they're drawn in the same way. Right? So the order of the vertices of the neighbors of each root matters. Is it clear, or Any questions? Thanks. Okay, so if there's no questions, then I'm going to ask a question, which is how many rooted plane trees on n vertices, and I want to count them up to this, you know, up to rooted plane tree isomorphism. And so let me try. As usual, we're gonna try some examples. So maybe let's say n is equal to 1, you get one tree, which just consists of a root. And notice that the vertices are going to be unlabeled, right? So unlike our previous examples. If n is equal to 2, then how many trees am I going to get? One. Yeah, okay, thank you. That is correct. I still get one tree, which looks like this. So I have a root, and it's connected to a single vertex, because the tree has to be connected. Okay, what about n equals to 3? All right, I have 3 trees. Well, actually, okay, let's see. So I can have one tree like this, and I can also have a tree like this. Oh, 2. Okay, yeah, that's right. So the answer is 2, right? I cannot draw any other trees that would be different from either of these. So the answer is 2 trees. And if I do the same for n equals to 4, how many am I going to get? 3. Okay, interesting. Yeah, let me try to draw, because I can do one tree like this, or I can do a tree like this maybe, or I can also do a tree, yeah, maybe, let's say even I can try. Okay, so I have 3 trees. Any more trees? Yes. Yes, there's more trees. How many more? 2 more. Okay. Indeed, yes, that is correct. I can have a tree that looks like this, and I can also have a tree that looks like this. So the roots are on top always. And notice that these two are not isomorphic. Because yeah, actually, and these two are not isomorphic as rooted plane trees. So anyways, the answer is 5 trees. And that is suggestive. Really thought it was Fibonacci for a second. Okay, yeah. Whenever you see 1, 1, 2, you either get Fibonacci or Cadman. And this time, yeah, I guess that's the theorem. The number of rooted plane trees on n vertices. Well, even on n plus 1, and let me do n plus 1 vertices, is the Catalan number Cn. Because usually you have n equals to 4, and this corresponds to 5 trees, which 5 is C3, which is 1/3 times 6 choose 3. If I'm correct. What 1/4? Okay. Yeah. So, anyways, that's the theorem, and how to prove the theorem. Can we somehow think of this as the number of ways to put parentheses in the ordered set? I mean, that's the somehow, yes. I mean, somehow, because all of these Catalan objects have to be in bijection. So the game here is to try to figure out what's going to be the correct set to biject with, and well, okay. So I want to do parentheses, and this is actually. I mean, what I'm going to do is Dyck paths, but it's Dyck paths are very easily converted into. You have a Dyck path that goes up, 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 right, right, up, right, up, right, 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 like this. And then it corresponds to a parenthesis sequence which has 4 opening parentheses, and then 2 closing, 1 opening, 1 closing, 1 opening, and then 3 closing. So I just kind of rid of the up steps correspond to opening parentheses, and the right steps to closing parentheses. So anyways, the idea is to goal is to find a bijection. Find a bijection which sends a tree to a Dyck path. This is rooted plane tree. And this is a Dyck path. And so it has n plus 1 vertices. And this is Dyck path from 0, 0 to n comma n. So, and the kind of, basically the key is to look at where your Dyck path, because it's, whoops. The key is to look at where your Dyck path touches the diagonal. The places where the subpaths between the touch points on the diagonal are going to correspond to the subtrees of which are connected to the root. So that's the idea. And so let's say I have a tree T, T1, T2, all the way up to Tk. It's a rooted plane tree. And then how do I define this Dyck path P of t? And the goal is, well, what I'm going to do is I'm going to consider 2 cases. Define P of t recursively as follows. So if k is, first of all, k, which is the number of, it's the degree of the root. And if k is bigger than 1, that means that your Dyck path is going to touch the diagonal. P of t touches the diagonal exactly k minus 1 times. Namely it is, so what I'm going to do is I'm going to do this. So let P of t prime, let Ti prime be obtained from Ti by adding a root, just an extra root. So I have my tree, maybe it looks like this. That's T. Then I'm gonna split it into subtrees, and then I'm gonna add an extra root to each individual subtree. And this is going to be T1 prime, this is going to be T2 prime, this is going to be T3 prime, right? And then I'm gonna, and the kind of the key observation here is that each Ti prime has strictly less vertices, strictly fewer vertices than T. And the reason is that the number of such trees is more than one. If it was just one tree, then you wouldn't get fewer vertices. So you just set P of T to be equal to just the concatenation of P of T1 prime, etc., all the way up to P of Tk prime. So the Dyck path you're going to get is going to look something like this. This is going to be P of T1 prime, and then, okay, this is going to be P of T2 prime, and etc. all the way up to this is going to be P of Tk prime. All right, and each of them, and all I have to do is I have to explain what happens if k is equal to 1, and then I'm going to do something different. If k is equal to 1, then so t looks like this. It has a root which is connected to a single vertex, and then there is some smaller tree t prime. And then the Dyck path, so P of t is just by definition the north step, then P of t prime, and then the east step. Yeah, let me write down north, then the east step. Okay, so you just kind of draw one north step and one east step at the beginning and at the end, and then the rest is this is P of t prime. Again, t prime is a smaller tree than t, so my recursion kind of works correctly. And okay, I have 1 more minute. Oh, I actually have 5 seconds. All right, yeah, I guess I'm gonna explain this next time. Next time we'll show that this is a bijection. And I'm also going to do some other stuff as well. Well, okay, sorry, that's not the end of the proof. Yeah, anyways, if you have any questions, let me know. If not, I will see you all on Friday, which will be the last lecture. Thanks.